Solubility rules. You need to memorize these. I have some mnemonic devices to help you memorize them. So rule 1, any group 1 metal, which are called the alkali metals, or ammonium salts are always going to be soluble. Just a reminder, a salt is any ionic compound that is not an acid or a base. So it's a whole host of substances. It's not just NaCl. Okay? So anything with group 1, alkali metal, or ammonium is going to be soluble. There's one exception, which I'll talk about when I get to rule 6. Rule number 2, this is where we're going to see our first mnemonic device. But the halogens, chlorine, bromine, iodine, and fluorine really as well, are soluble except when they're with one of those 3, silver, mercury, and lead. So I call these the halides because they are the halogens in ion form. And remember, when you form an ion of a halogen, its ending becomes IDE, so halogen becomes halide. All right, so my mnemonic device here, and I did receive this mnemonic device from somebody who teaches out in Texas. So it references the Texas A&M mascot. So if you can come up with something better that makes sense, that fits the mnemonic device, please share it with me as long as it's school appropriate. Okay, shh. So, Hal hugs Aggies pretty badly. Now let me show you how this mnemonic device works. Okay, so Hal represents the halides or the halogens, right? Hugs, Hg, there's mercury. Aggies, Ag, that's silver. Pretty badly is lead. Okay? So, any other chlorine, bromine, iodine, salt with any other metal will be soluble except for those 3. Cool? Moving on. You can pretty much ignore rule 3 because it kind of gets lumped in with the other halogens, and we don't really deal with fluorides that much. Okay? 4. Rule number 4. This one's an important one. Actually, they're all important, but this one's a big one. Rule 4. Nitrates, chlorates, perchlorates, and acetates are all soluble. Period. End of discussion. Nitrates, chlorates, perchlorates, and acetates are always soluble. Okay? The big ones you're going to see here are the nitrates and the acetates. Those are the ones we see the most often. Acetate is just written in a slightly different format there. You can also write it as C2H3O2 minus. Okay? Rule number 5. This one's going to be where our next mnemonic device is. Sulfates are soluble except for those 6 exceptions. Okay? My mnemonic device for this one is long, but it's sully, can, bag, hags, pretty badly, in Sri Lanka and Argentina. I'm providing these tools if you want to use them or not. I don't care. Okay? So, sully, sulfate, yeah. Can, there's calcium. Bag, barium. Hags, Hg, that's mercury. Pretty badly is lead. Sri Lanka is strontium, and Argentina is silver. Okay? All right. And then the last rule, number 6, those things are going to be insoluble except the fact that rule 1 does take priority. So if you have any of these with one of the rule 1 substances, they're going to be insoluble. Or sorry, if you have any of them with a rule 1 substance, it will be soluble. Otherwise, it's insoluble. The one exception is oxides. Always insoluble. Always. Always. Okay? So like I said, you do need to memorize these rules. But let's do some practice with them. So if you turn to your in-class problems, to this page, take a moment to go through and identify the solubility of all of those. All right, so silver nitrate. First of all, what is the formula for silver nitrate? AgNO3. Soluble or insoluble? Soluble. That's not how you spell soluble. Soluble. Remember, all nitrates are soluble, regardless of the metal it's with. All nitrates are soluble. Sodium chloride, how do we write that? NaCl. Soluble or insoluble? Soluble. Some of you, most of you, not all, but most of you had that opportunity to demonstrate the solubility of sodium chloride last class. Not everyone had that in their procedure. All right, lead 2 bromide. What's that formula? PbBr2. What's the solubility? Insoluble. It's a halogen with lead, so it's insoluble. Okay. What is the formula for ammonium hydroxide? NH4OH. Solubility? Soluble. Soluble. Remember, with hydroxides, that was rule 6. Rule 1 takes priority. So since ammonium was part of rule 1, it's soluble. Okay. Barium sulfate, what's the chemical formula? BaSO4. And the solubility? Insoluble. That was rule 5. Sulfates with barium and then 5 others are insoluble. It's one of those exceptions for sulfate. Calcium hydroxide, what's the formula? Insoluble. We'll learn in a later unit that this one is moderately soluble, that it has a fairly high solubility product constant, but for right now, we're not worrying about that. We're just going based off of the solubility rules. And then lithium carbonate. What's the chemical formula? Li2CO3, soluble. Carbonates are mostly insoluble except for rule 1. Those alkali metals and ammonium. Okay? So make sure you are memorizing these solubility rules, and really the best way to memorize them is just to do practice problems. Okay? And we're mainly going to see this in things called net ionic equations, which is what we're going to go over now. Some of you may have learned about net ionic equations in previous years, in a previous class, but some of you haven't. They're going to start off the same way we've written reactions up until this point. Okay, so let's just do the plain old, regular chemical equation for this one. Okay, that's going to be called the molecular equation. So we're going to write the chemical formula for potassium chloride, which is KCl. What state of matter do you think KCl has? Yep, aqueous or aqueous. You can pronounce it either way. This problem actually should say solutions of potassium chloride and lead 2 nitrate are mixed. Don't worry, on your homework and on your tests, quizzes, all that stuff, it will be really clear at the beginning. Okay, like it'll be really clear if you're mixing solutions or if you have them in a solid form or whatever. You will have to figure out the states of matter of the products. Okay. All right. So this is mixed with lead 2 nitrate. How do I write that formula? PbNO3 Don't forget to put parentheses around NO3. And this one's also aqueous because it's a solution. Now we're going to figure out the products. What type of reaction is that? That's a double replacement or double displacement. Either one is fine. In this type of reaction, the cations switch their partners. Okay? So potassium will be with nitrate and lead will be with chloride. All right, so what is the formula for one of our products? KNO3. Does it matter which product we write first? Nope. We'll identify this state of matter in just a little bit, so I'm just going to leave that blank for right now. And what's my other product? PbCl2. Now, think back to your solubility rules, which you've memorized in the last 5 minutes. And KNO3, is that soluble or insoluble? Soluble. So therefore, what state of matter would it have? Aqueous or aqueous. Again, you can say either one. I say aqueous. Some people say aqueous. Tomato, tomato. Aluminum, aluminium. It's whatever, okay? PbCl2. Solid, because it's insoluble. Therefore, it won't dissolve, and it'll produce as a solid. What do we call that when something produces a solid? That's a precipitate. Okay, that's why these are called precipitation reactions. Okay, so it's a precipitate. That's an indication that a chemical change has taken place. Okay, so what do you think we're going to do with this reaction next? Balance it. So go ahead and take a moment to balance it. That's why I left the little lines in front, so we remembered to balance them. Have we balanced it? All right, what are the coefficients when this is balanced? 2, 1, 2, 1. All right. So now, we are going to write something called the complete ionic equation. So for this, what we're going to do, for the complete ionic equation, in order to get there, we're going to dissociate any aqueous strong electrolytes. Okay? So anything that's aqueous and is also a strong electrolyte, we're going to dissociate. What does dissociate mean? Separate into the ions, or split up back into its ions, break up into its ions, however you want to say it. So anything that's aqueous and a strong electrolyte. I'm being really specific in what I say because sometimes we have things that are aqueous that aren't strong electrolytes, and those don't dissociate. For example, if we had sugar up here, that doesn't dissociate because it doesn't break up into any ions, okay, because it stays as one thing, okay? Also, weak acids and weak bases, those are weak electrolytes. They would not dissociate, because remember, they only partially dissociate in solution. So we would not break them up, okay? And also any insoluble substances we would not break up because they're not aqueous. Okay. So, looking at that, would KCl dissociate? Yes, because it's aqueous and a strong electrolyte. When we write the complete ionic equation, we're also going to maintain the balancing that was there, okay? So this would break up into 2K plus and 2Cl minus. Okay. Now for this ionic equation part, the complete ionic equation, I'm never going to grade that. Okay. If this was a test question, I would be looking at the molecular and the net, and those instructions would be on the test. So the ionic equation is the complete ionic is more for your benefit to help you get from the molecular to the net. So therefore, to save some space and time, don't worry about the states of matter for your ions in the ionic equation. P.S. Anything that's an ion has to be aqueous, because that's the only way it can be in solution is if it would dissolve. Okay. What would PbNO32 do? Would it dissociate? Yes, it would dissociate into? Exactly. Now, no one's asked this yet, but let me explain. Or what were you about to ask?
Is there a reason you don't use equilibrium?
Because we're not there yet in the year. That's not what I was getting at, though. No one's asked this yet, and that is, does it matter if we write it as PB2 plus or PB plus 2? So the answer to that is, for College Board, no. For my class, no. But there is a difference. And you might have some teachers, maybe off in college or at somewhere else, that they are going to be particular about it. But there is a difference. And the difference has to do with, if it's a charge, like what we have here, it's the number then the sign. If it is an oxidation state, which we'll talk about in a few classes, it's the sign then the number. So really just, it's the differentiation between if it's an oxidation state or if it's a charge. Okay? I will always write it the correct way. You should probably get in the habit of doing it, but if you slip up, it's not the end of the world. You're not going to lose points. Okay? Now, if you don't write a charge at all and there's supposed to be a charge, that's different. That will cause you to lose points. Okay? So, on the product side, KNO3, does it dissociate? Yep, what does it dissociate into? And then PbCl2. No, it does not dissociate because it's a solid, so we're going to keep that together. And I always keep my state of matter for my precipitates just so I don't lose them. Okay? Now, for the net ionic equation, how many of you have a job that you're paid for? Or you've had a job that you're paid for? Okay. Have you ever looked at your pay stub and you see your gross income and then your net income? What's the difference between them? So yeah, the taxes. The taxes are what's the difference between them. So your gross income is what you were paid. And then they take out all these taxes and fees, and if you have a full-time job, you might have health care benefits, stuff like that. And then your net is what you actually get deposited in the bank. That's what you get to take home at the end of the day. All right? So it's similar to that, where the net here, the net ionic equation, is the actual reaction that's occurring. Okay? So, looking at the complete ionic equation, we're going to look for things that didn't change from one side to the other, because they're not participating. They're called spectator ions. For example, 2K plus is the exact same on both sides. It did not change state of matter. It didn't change, it stayed the exact same. So it cancels out. What is our other spectator ion here? The NO3 minus. That also cancels out. And then whatever's left over is our net ionic equation. Now remember, am I grading the net ionic? Yes, so make sure you include states of matter for all substances in your molecular and your net ionic equations. Are you asking, is there a difference if you write the PB before the CL? No, it's the commutative property. 2 plus 4 is the same as 4 plus 2. It does matter for your compounds, but it does not matter in the order of your reactants. No, nah, same thing. Just representation of what's happening in that reaction. Okay, so now this is the actual reaction that's occurring, because both the lead and the chloride formed up and formed a precipitate, which is getting locked up in solution. They're actually changing state of matter from the left to the right. They're changing properties. That's the chemical change that's taking place. The potassium and the nitrate here are my spectator ions. What do spectators do at a sporting event? They just watch. They don't participate. So they're just there, but they're not doing anything. Okay? Only those that change from one side to the other do something. So they're what go in the net ionic equation. Let's do the next one. Silver nitrate and magnesium bromide are mixed. And again, we're going to assume that both of these are solutions. So for my molecular equation, how do I write silver nitrate? Magnesium bromide. What type of reaction is this one? Double replacement again. All of these precipitation reactions are going to be double replacement. And even the acid-base reactions we're going to get to in a little bit will also be precipitation reactions. Okay? So, or not precipitation, will be double replacement. All the reactions we're doing today are double replacement reactions. So, what are my products of this reaction? Stop trying to balance it. Stop trying to balance it and give me the product. Just give me the product. AgBr, we'll get the state of matter in just a little bit. And then my other product? MgNO32. Now, let's identify those states of matter and then balance it. Yeah, try not to do too much at once because that's where you get tripped up. Okay? Yep, because it is a halogen with silver, so that is a solid. And then magnesium nitrate? Aqueous. All nitrates are soluble, period. Okay. When this is balanced, what are the coefficients? All right, 2, 1, 2, 1. Which of these substances are we going to dissociate? Everything except for the AgBr, right? And we're going to maintain the balancing as well. So we'll have 2Ag plus 2NO3 minus plus Mg2 plus 2Br minus, forming the AgBr is not breaking up because it's my what? Or precipitate. And Mg2 plus 2NO3 minus. For this reaction, what are my spectator ions? The magnesium and the nitrate. See how magnesium stays the same, so that's going to cancel out. And the same thing with my nitrate. So my net ionic equation is 2Ag plus aqueous plus 2Br minus aqueous goes to 2AgBr solid. Okay. Why don't you guys try the third one, which is at the top of your next page, on your own. All right, so now that you have had an opportunity to complete this one, let's talk about it. So let's write the molecular equation. What are my reactants? NaCl plus Li2SO4, both of those are aqueous, goes to Na2SO4, which is aqueous, plus LiCl, which is aqueous, because both of those are soluble. So when this is balanced, what are my coefficients? Put 2 in front of both the NaCl and the LiCl. All right, so now when we write the complete ionic, which remember, that's just like your scratch work in between. You don't actually have to write the complete ionic. Some of you will get really good at these. You can go straight from the molecular to the net, though I will leave space for you to do the complete ionic if you want to, but I won't be grading it. Okay? What breaks up? All of them, right? All things dissociate for this equation. So what are my spectators? Everything. So everything ends up canceling out, right? So what's my reaction? There is no reaction. So that's what you write for your net ionic for situations like this. Because if they're all spectators, there's nothing participating. Therefore, no reaction. Okay? So if this were a test question, you would write the molecular, and then for the net, you would write no reaction. Okay? Just be aware that sometimes that does happen as well. Yes? That or a substance changing state of matter. Like, because when we get to our acid-base reactions, you don't always have to have a precipitate form for it to be a reaction. Just something has to go from being like aqueous in a compound or aqueous by itself, or maybe a liquid's being formed like water. But since it's all aqueous, it's all ions, these products, we would never actually get them. How would we be able to isolate the Na2SO4 from this? We really can't because it's not being locked up as a solid or as a different state of matter. It's still all dissolved. Really, if you did this reaction, you would just have a beaker of water with a bunch of these ions floating around. You have no way to know if a new substance forms or not. Okay? All right, so now, neutralization reactions. I said before that these neutralization reactions are also going to be double replacement. Now, in a neutralization reaction, we have an acid and a base reacting together to form some sort of salt and water. There we go, finally. So acid base forms salt and water. And the salt does not necessarily have to be NaCl. It's only going to be NaCl when you have some sort of sodium hydroxide and hydrochloric acid. Okay. So with this one, let's write the molecular equation. How do I write sodium hydroxide? NaOH. Is that aqueous? Yep. It's mixed with phosphoric acid, H3PO4, aqueous. Na3PO4, yep, that is aqueous. Because it's rule 6, but rule 1 takes priority. H2O is a liquid. Aqueous means that you're dissolved in water. You cannot be dissolved in it in yourself. Okay, liquid is water is a liquid. Now, we can go ahead and balance this, and then I'll talk before we get to the ionic equation. What? What was your last one you said? Wrong. 3, 1, 1, 3. Sometimes it helps to think of water as HOH, because then you can balance the hydrogen and the hydroxide. Okay, if you think of this as being HOH, we'll balance this hydrogen with this, and the hydroxide with this. All right, what type of base is sodium hydroxide? Strong base. And what type of acid is phosphoric acid? Weak acid. Weak acid. So remember, weak acids are what type of electrolytes? Weak electrolytes. Weak electrolytes, like weak acids and weak bases, weak acids and weak bases only partially dissociate in water. So when we write the equations with them, we do not show its dissociation because it's only barely happening. They're only dissociating like less than 10%. Okay? Break doesn't have an E at the end.
Okay. So, not only is that anything, I think either one in the equation is
Right. Like if you have a weak acid or a weak base, or both, you don't dissociate them in the equations because they're only barely dissociating. Okay? So even though it's aqueous, our phosphoric acid is not going to be dissociated, which is why previously I was saying that only aqueous strong electrolytes get dissociated. These weak acids and weak bases are weak electrolytes, so we don't dissociate them. So for our net ionic equation, or sorry, for our complete ionic equation, are we going to dissociate the sodium hydroxide? Yes, because it's a strong base. So it would dissociate, like we were doing before, 3Na plus 3OH minus. What about my H3PO4? You leave it together. And since I left that together, I'm going to still indicate that even though it's still aqueous, think of it, it acts kind of like a covalent compound, where it still dissolves, it's just not dissociating. Okay. Na3PO4, does that dissociate? Yeah, it's a salt that's aqueous, so it's good to go. So that dissociates into 3Na plus PO4 3 minus. I'm going to erase this HOH because it's in my way. All right. And then water, do we dissociate that? No, it's a liquid. It's not aqueous at all. So H2O liquid. So what is my spectator ion for this problem? My Na plus. My sodium ion, that's my only spectator. Okay? So everything else just comes back down. We add back in those states of matter. Well, I mean, here it's combined with something and it's aqueous.
Well, that's because it's the new one. Like when it's combined with something that's not used.
If it's not a strong base, it's not going to be aqueous. If it's not, if hydroxide's not a strong base, it's going to be insoluble.
Yeah.
Pretty much.
So, but by itself, it's aqueous?
Any ion by itself, the definition of it, like in order for it to be in ion form in a solution, it has to be aqueous because that's the only way you can get the ion. Okay? Questions on that one? Try the next one on your own. All right, so now that you have a chance or have had a chance to do this one, what does this molecular equation look like? Or you can write it like that. Either one. Okay. Is that aqueous? What does it mix with? KOH, which is aqueous. What does that form? Potassium acetate, right? Which is aqueous. Remember, all acetates are going to be soluble. They're like our nitrates. Okay? And then water, which is a liquid. Okay. What will dissociate? The potassium hydroxide and the potassium acetate. Acetic acid is a weak acid. It doesn't dissociate. It's like our phosphoric acid in the previous problem. Okay? So, acetic acid stays together. Potassium hydroxide dissociates. Oh, by the way, we didn't talk about the balancing of this, but this one is already balanced to begin with. It's 1 to 1. Potassium acetate will dissociate. And water doesn't. Liquids will never dissociate. You have to be aqueous to dissociate. So our net ionic equation, what cancels? Potassium. That's our spectator. And that's the only one. And then C2H3O2 minus plus H2O liquid. Okay? So that's it for net ionic equations for today.